this will never work, never. I'm pretty sure already, like in my case, the book review,
audio
is first already. Always. I feel like there's always at least something that like
It doesn't play when you plug your laptop.
You can only
Like it doesn't. Yeah, no, but it doesn't play here.
I really like they don't do much information.
I have this sound.
I mean, this is the most unified thing. Join the staff.
Is it on? Oh, yes, it's on. Should we start? Yes. Okay.
Yes.
We start. Hi everybody, welcome back after hiatus from this event of Astronomy on Tap, the May edition. Today we have two speakers with us, but first of all I want to introduce you to our team. Here we have the tech crew. That's going to take care of everything technical. And we are missing people actually. But the social media people that are not here, and me, I am the host of the event. My name is Valentina. Nice to meet you. Thank you. And well, yeah, today we have two speakers. The first one, okay, you have already your slides here. The first one is Daan Meerburg. He is a professor from the University of Groningen. He is from the institute, I forgot the name, the particle physics. Institute of Particle Physics and all this. So he's going to talk to us about cosmology. So please.
I'm going to start.
Yes.
Thanks a lot.
Oh, we're doing these up?
Does it work? It died straight away.
It's on though. Correct, the light is on.
Oh, okay.
It's on when the light is on.
Tap the microphone maybe a bit.
Okay. All right. Well, thanks for giving me this opportunity to tell you something about cosmology. I'm super excited about this. In fact, I would say I'm so excited about this that I contacted the organizers 2 years ago. They got back to me after a year, and then a year later I was finally allowed to give a talk. So I'll actually run you through a crash course in cosmology, and by the end of this talk, I hope that you can explain to all your friends why we are pretty confident that there was a Big Bang, and that most of the stuff in our universe is actually dark energy and dark matter. And I'm pretty sure, given that you're here, that you have some keen interest in this topic. And of course, there's already many astronomers here and physicists and some students. So I'm sure that you have some interest in this topic. And I'm also sure that during an evening with your friends or with your family, you had a situation where your crackpot uncle said, okay, what about this universe? And you said, well, there's dark matter and dark energy, and the crackpot uncle would say, how do you know, right? And you're like, well, because the scientists tell me so. So that's, of course, the ideal moment where the crackpot uncle will tell you what a pot of baloney. So here, hopefully by the end of this talk, you'll be confident enough to tell them, this is the way it works, and we have quite significant evidence. And so one of the key things that was already discovered in 1929 by Edwin Hubble was the fact that the universe seems to be expanding. And this famous measurement shows you the distance towards what he at the time called nebula, but nowadays we know that these are galaxies, as they, and it turns out that these nebula, the further they are away, so the more distant they are, the faster they are moving away from us. Right? So I actually brought my own little experiment here, which is, I guess, quite familiar to some of you, right? This is what a theoretical physicist does as an experiment. It inflates a balloon. But just imagine that the universe is confined to the surface of this balloon. Then I drew a bunch of dots on this balloon, and they represent galaxies. And so if I inflate the balloon, as you can see, the dots move away from one another. Now this is one way, but obviously it also means that if we go back to the past, right, what happens is that these dots, these galaxies, come closer together, and you collect mass, and the density in the universe starts to increase. And so one of the predictions that was made by George Gamow in 1948 in this famous Nature paper is that indeed, if the universe is expanding, it must have been much denser in the past. At some point, so dense that it was kind of like the sun, right? So, but then throughout the universe. So the surface of the sun throughout the universe. And he argued that if that was the case, then there must be some kind of radiate afterglow, very similar to how the sun is radiating. There must be some particles of light coming from this event. And just to show you how this works, I have this video here. So imagine you going very far back into time when the universe is very hot and very dense, and basically consisted out of what we call free electrons, which are the negatively charged elementary particles, and protons, which are positively charged. And in this particular drawing here, the red blobs are the protons, and the green dots are the electrons. And it turns out that light mostly interacts with free electrons, so with electrons that are not bound to a particular molecule. And so what happens if I play this video is that in the early universe you have these particles of light which are drawn in blue. They bounce off of these free electrons. But at some point the universe cools enough sufficiently that these electrons and protons form hydrogen. And at that moment the universe becomes transparent, and this is exactly when this light is formed. And this light is known as the cosmic microwave background. And in principle, this light has been able to travel pretty much unimpededly towards our telescopes. And in fact, this light was discovered by Penzias and Wilson quite by accident, and that's a whole, next time you invite me, you can talk at least an hour about that. Quite by coincidence, in 1964 by these people, and they found that this radiation was coming from all directions. So that's why they were quite confused about it. They were trying to look for some radiation that because they were working at this laboratory, Bell Laboratories, and were trying to look for sources of confusion, and they found this afterglow. And this afterglow now is very cold, right? So if you have roughly 3 Kelvin, which means it's almost 270 degrees Celsius below zero as we measure it in Celsius. What is also here, so I draw this kind of fake observation, right? Obviously this is in microwaves, and we can't see microwaves, and so therefore whenever you see a picture of the background, it's always false colors, right? So these are not real colors, we can't see it by eye, but just to show you what it looks like. So it looks kind of like, homogeneously. Now, again, for those of you who are not familiar with these kind of figures, and we have a lot in cosmology, just let me kind of show you what this means. So here's a video of Earth, and as we observe the entire universe around us, we can project this universe, which is really like a sphere. We can project this on a surface, and if we do, it becomes this oval-shaped observation. And you see here the galaxy in the center, and we can move, we can change the frequency of observations all the way from optical up to microwave, right? So in this case, microwaves means longer wavelengths. And here we have the same kind of observation, and it looks very homogeneous and isotropic, which means it looks the same in all directions. And it has this average temperature of about 3 Kelvin. So it's very cold. Now, what happens if we increase the contrast ratio? We start to see all kinds of structure in here. So here again you have the galaxy, but there's all these other things. So you have these blue and green spots and red spots, And these are all deviations from this average temperature. So this average temperature of 3 Kelvin is what we observe, but on top of that there's these tiny variations. Right? These turn out to be key to what I'm going to talk about next, and in order to convince your crackpot uncle eventually. So here is the latest and greatest observations that we did with this Planck satellite. I was part of that collaboration, and as you can see here, again it's the same figure. For some crazy reason, depending on the collaboration, we changed the color palette of our program, and so sometimes it's blue, and sometimes it's green, and sometimes it's red, but it's the same thing, right? So in this case, it's still just the slight variation with respect to this background temperature. It's all across the sky, and here again is the galaxy. And so how do we learn about, for example, the fact that there is dark matter and dark energy? We can learn that, right? So these are the kind of things we can infer from these fluctuations. What are the constituents of the universe? So what's the universe made out of? What are the densities? What's the current age of the universe? And what happened right after the Big Bang, right? So these are things we can learn directly from these small variations. And we do so by looking at statistical properties of these hot and cold spots, if you will, right? So that's kind of the key message. And I'm going to train you in the next 5 minutes how we do that, right? So that's, hold on, right? So what I'm showing here is just a snapshot of that giant picture we saw before. So this is just a square taken from the full sky. And what I'm showing here is a simulation, which was done by one of my students. And what is shown here is what we think the universe looks like for what we call standard cosmology, so our best estimate of what the universe is. If I change the amount of matter, right, these fluctuations change. So I can see that by eye, right? So these fluctuations are sensitive to the amount of matter in the universe. I could do something similar if I change the age. So again, this is our standard universe, but if I change the age of the universe, you see that these fluctuations change. It's very subtle this time. And I can do the same when I change the initial conditions. So if I change, for example, how the universe came into existence, which is quite a remarkable statement, then again, these fluctuations can change. Now, obviously, this is not how we do cosmology, right? We're not sitting down in front of our screens and trying to figure out how these changes appear and then tell, okay, that means that there's, 4% variance. Yeah, that's not how it works. So in order to do this better, we actually look at certain statistics. And the key measurements in measuring these, or that are extremely sensitive to the structure of these fluctuations, is what is known as a power spectrum. Now, let me stress, like the power spectrum, explaining that to, let's say a third-year student in astronomy or in physics would take me, let's say, 10 lectures, right, to explain it in detail. So I don't want you to understand all the details. What I want you to show is visualize how this power spectrum comes about and how it's related to these fluctuations. And one nice way of doing that is by breaking down this CMB map into a sum of individual maps. And hopefully that will be clear in the next video. So in this video, you see a bunch of maps, which are kind of together constitute the full map. And they have different structure on what I call different scale, right? So basically, this is a large mountain range, this is a smaller mountain range, etc., etc. And as I move through these different maps, as I'll show you, I'm probing different parts of this figure here, which is what is called the power spectrum. So here I'm probing large scales, so these are large fluctuations. These are smaller fluctuations, right? And they're probing a different part here. And I can go to even smaller scales, probing yet another part, etc., etc., right? So basically it's following this whole figure right here. And in the end, when you sum all these individual maps together, then it turns out to be the same map as I put in, right? The actual sky that we observe in the CMB. I'm going to run this video till the end because then it'll show that to combine these are indeed the true map. And that's the kind of statistic, so it's clear that the statistic is sensitive to the structure because it's following the structure as we move through different size fluctuations. Now we sum all these together, we get the original map back, right? So that's the idea. So this is our CMB map. Now this is a little misleading because we took out the galaxy. but that's just the idea. And now I'm going to show you two videos, which basically again show you the actual map, the realization on the right-hand side, and it shows you exactly where that is in the power spectrum. And there's even a sound, so it going from large scales, low sound, or low pitch, to high sound, right, to small scales. And as you can see, right, you see the structure changing in this map, but you also see that the total power kind of decays, right, it moves away. You hardly see it. That's because the power here goes down, right, the amplitude goes down. So that's how we see this. We can do the same thing, but now for the cumulative result, so it's the same story, now I'm adding up all the different maps, and then on the right-hand side, you see what looks pretty much like our actual universe, right, that we observe in this back. So that's how it works, right? So now I've trained you, you should be able to do this, and you have to prove that to me. So this is exercise number 1. And hopefully this will come back in the quiz later. I'm not sure if you put it in, but if not, then it will be a bonus question. And so what you see here are different maps, A, B, C, D, and E, and they actually correspond to different power spectra, right? So different scales and different power, different amplitude. And to give you a hint, right, this particular map here, number E, has kind of a single scale, right? Everything is around the same scale and one power. So very evidently, I'm going to ask the audience, what should E correspond to? Raise your hand if you know the answer. I already told you, right? So there's some students. There we go. Yes. Please, we have one professor got it right. Yeah, so E belongs to 4. So think about this carefully. We'll come back in the quiz. And I think at least 3 of the 4 questions will have E4 in it. So you know that at least one is right, wrong. And so what I'm going to show you in these final 3 slides is how this power spectrum, this very sensitive statistic, so the one that we don't have to sit in front of our TV and then see how the CD change, but we actually use this power spectrum. And what I've shown here in blue is our actual measurements. So these are actual measurements, which are extremely good, right? So we have exquisite measurements of this power spectrum. And what I show in red is how this power spectrum changes if I change the amount of matter into it. And it's significant, right? So if I change the amount of matter, I go straight through this plot. So evidently, right, this cannot be the true value, right? So it has to be really, fall within these error ranges. And I can do the same thing for the amount of dark energy. So if I change the amount of dark energy, this plot changes and significantly. So we're pretty confident about the amount of dark energy. If you change the initial conditions, I can do the same. This whole figure changes a lot while we have these exquisite measurements, so it has to be somewhere around here, right? So that's the power, that's how we do cosmology, right? Almost by eye, right? And so what have we learned from this? Now it turns out that we measure these power spectra to high precision, and we've learned that we can actually describe our entire universe with very limited number of parameters, with almost only 6 parameters. And of those parameters, it turns out that 2 of them are stuff we don't know, right? Dark matter. So we've learned that from measuring these power spectra. And that there's something that we call dark energy. At the same time, we don't quite know how the universe came into existence. Although the most well-supported paradigm is something known as inflation, that some of you might have heard of. But that's the leading candidate. But for all of these things, we don't quite know, A, what they are. We don't know what dark energy or dark matter is, and we don't exactly know how inflation came to be. So a lot of open questions remain for all of you to answer. Thank you.
Okay, any questions from the audience? We have gifts if you ask a question. Yes.
It was something I was thinking when you, the low pitch and the high pitch with the sounds and everything. So what I don't know is that when you have a high pitch, you have high energy, and when you have a low pitch, you have low energy, but in some way it was different when you said it. So am I?
No, yeah. So this whole pitch is just to show you that you're going to. I mean, it's really, trying to kind of gimmick this idea of what the people in gravitational waves physics do. I think the people that made the video thought about it carefully and say, well, we make this quirking sound. Maybe we'll collect a lot of attention. I think. I don't know what it is.
Okay, it's confusing me.
Okay, yeah, but it's just showing that small scales obviously represent higher frequency and therefore higher pitch.
All right.
Yeah.
Well, okay.
That's the line of thought.
All right. Yeah.
Any other question? Are you sure you're not going to get a nice sticker? Yes. We have another. Is it the nominal?
Yeah.
Okay.
So I was wondering how could you distinguish between this kind of models with dark matter and models where you modify gravity instead of using dark matter?
That's a very good question. So I guess maybe the slightly uninformed audience, right? So dark matter is a kind of matter that only interacts through gravity, yeah. And so in order to create very similar effects, instead of saying, well, there's an additional type of matter that only interacts through gravity, why not change gravity altogether, right? That's the idea of what is called modified gravity. And one of the things so modified gravity tends to work mostly trying to explain, let's say the rotation curves of galaxies. But it's much harder to put in modified gravity in these theories because modified gravity, I think, naturally, the kind of simplest model that you have, don't necessarily create the right conditions to form the first galaxies. And that's what you see in these particular observations. So you see that dark matter plays a critical role in building up the necessary gravitational potential to eventually lead to the structure that we observe today. So if you modify gravity, you have to also account for that in some way. Yes, hopefully that helps.
Any other question? Yes.
Right here.
Yeah, you talked about the expanding universe. I was just wondering if there's any reason to assume that there could be a limit to that, physical limit.
You mean that stops expanding?
Exactly. Yeah.
So of course if you look at how we know that, well, first of all, we know we have these observations that therefore we conclude that they expand. But in principle, the solutions to the theory allow you to have the universe to eventually collapse as well. That's a possibility. But we don't see any evidence for that right now in today's time. That's a good question, yeah. But it's definitely a possibility.
Any other? No. Then we thank again the speaker. Very nice talk. And now we go on a break, so everybody can get a refill in their beer glasses, and then we continue with the next talk. See you later.
Music.
we're going to continue now with the second speaker, Mariano Méndez. He's also professor at the University of Groningen. He's actually my boss, so be nice. Please. Thank you. And yeah, well, please, go ahead.
I'm her boss. This is working, right? I'm her boss, but she asked for applause for Daan and not for me, but I'll forgive her. Okay, I'm Mariano Méndez. I'm professor of astronomy. I'm a bit embarrassed because I see some of my students coming back. I will talk to you today shortly about what black holes are, how can you see them even if they are black holes, and the story is about someone coming from Argentina, the Pampas. There is a big board there that says Pampero, and there is a cowboys there. Those are the gauchos where they come from. So the whole story started with Newton in 1687 when he was sitting under the tree in Cambridge, says the history, and then he was sleeping, having a nap, and then a little apple came onto his head. Sorry, I need to stand here because I don't have that stand, I'm not so tech. And he had a brilliant idea that gravity is a force that works like this. The force is proportional, this is a constant to the masses. Two masses attract each other, and is inversely proportional to the distance squared. So that was fantastic, his waking up under the tree with this apple and realizing that, which is not how it happened, isn't it? He actually knew from a lot of measurements from Tycho Brahe before him. Someone called Kepler came up with 3 laws of the movements of the planets in the solar system, and then Newton deduced from those laws his formula. And I learned how to do that in my first year course physics. I was impressed. There is a consequence of that, of this force, because if things attract each other, I forgot to bring my apple. I always bring an apple, but let's take a grape. There is a force, because the force attracts, the force of the Earth attracts this grape. Normally I have an apple which is more impressive. It attracts this grape. The grape tends to fall. If I throw it up, it goes up. There is a lighting that doesn't allow me to. It goes up and then comes up. If I throw it high, stronger, it goes higher. When the roof is not too high, if I go it down, and then no one can eat it anymore. But if you were strong enough, I can do it later for you. I can throw, shoom, and it never comes back. It never comes back. And this is because from Newton's law, you can deduce there is a velocity that if you impart that velocity to an object on the surface of the Earth, it will never come back. And that velocity for the Earth is 11.2 kilometers per second, or about 40,000 kilometers per hour. 1,000 kilometers per hour. And to give you an idea how fast that is, I made this little animation. You start with the train, at time 0 in Groningen, in 4 seconds you are in Assen, and if you wait in 8 seconds you are in Zwolle, and in about now 15 seconds you are in Harderwijk, and then in Amersfoort, and then in 18 seconds you are in Amsterdam. So it's very fast. You can go there at that speed. You have to go 11.2 kilometers per second, or 40,000 kilometers per hour. So you can go from here to a party and come back very quickly. The only problem is that if there is a cow in the middle of the rails and the driver sees it here, he doesn't have time to stop if the cow is dead. So you have to be here. But anyway, that's how rockets try to escape the attraction of the Earth. A little bit after Newton, there came these two men. They did it almost simultaneously, although you would see that there are 15 years of difference. But at that time, that was simultaneous. There was no internet, so no one knew of what someone else was doing. There were no journals, or were not read, obviously, all around the world. So they did the discoveries independently. One in the UK and the other one in France. And they realized the following. They said, okay, if there is escape velocity, and the speed of light is not infinite, if I switch on the light now here, okay, you see it immediately, you think it's instantaneous, but all of you, or most of you, should know now that it's not true. But around that time, there was an astronomer called Romer who, measuring the satellites of Jupiter, realized that the calculations that you were doing of the orbit did not match. Something was failing. And the only explanation he could find is that if the satellites are at different distances from us, as the two planets and the satellites are moving around, the light has to travel longer distances, so the calculations will fail if I don't apply that correction. Another French called Rousseau measured the speed of light on Earth. And those two people were rejected by their directors. They said, they're crazy, this cannot be, light is instantaneous. But these people realized, at some point, people believe it, they realized that if there is escape velocity of the Earth, what if there was a star in the universe where the escape velocity was equal to the speed of light? What could happen in that case? Because I don't remember. And now the speed of light is 300,000 kilometers per second, not 11.2, but 300,000. So 1.1 billion kilometers per hour if I did the calculation correctly. But you have to move really fast to escape the attraction of an object that has that speed, escape velocity. So they didn't say that that object existed, but they hypothesized, that's the word, that it could exist. And if it existed, then light would not escape. That's what they thought. And so the same way that I throw a grape or an apple up and it comes back, the light would go up and come back and will never escape. They were wrong. Because the speed of light, it turned out later, it was realized by Einstein, the speed of light is absolute. It's always 300,000 kilometers. So it cannot go up, stop. The light does not stop and come back. Doesn't do that. But it loses energy. As it climbs against the potential energy of the object, a word that I hope people who study physics know, but if not, it's not really crucial. It's the attraction, if you want. As it goes up, it loses energy, so it becomes redder and redder and redder, and so red that eventually it's invisible. So the same would happen, but in a totally different way. It turned out that if you do the calculation that Einstein did, someone else did it, this guy called Karl Schwarzschild did it almost immediately after Einstein published his theory. This guy was thinking about that in the trenches in the First World War. He was German. And then, if you do the calculation, it turns out that the conclusions are the same as the one as Laplace and the other guy who I forgot the name, Lowell, I think it was, Mitchell, sorry, and, oh, it's there, Mitchell and Laplace, but it was, their calculations were wrong. But the numbers that came out are the same. So how big or how massive has something to be so that the escape velocity is equal to the speed of light? So it turns out that if you do the formula, I don't care too much, it depends on the ratio between the mass of the object and the size of the object. So the bigger the mass, the more attraction you have. And the smaller the radius, also the more attraction. Because if you remember the formula of Einstein, of Newton, there is a radius divided. You don't need to know math, but okay, believe me. So it turns out that the number, the magic number, is not really this exact number with all these decimals. In kilograms per meter, is that. Is the number of the devil. So if the mass of an object divided by its radius is that number, then the escape velocity would be the speed of light, and so light would not escape. So if you take the mass of the sun and you compress it to a sphere of this diameter, 6 kilometers, you would reach escape velocity from the sun that is equal to the speed of light. And if you do the same with the Earth, but now you compress it to a sphere of 2 centimeters, the same will happen, and the same with the moon if you make it 0.2 millimeters. So to be a black hole, the mass is not really what matters. What matters is the mass divided by the size. So I made a black hole. And I teach you how to do it. So you take the Earth, and you come with one of these machines. And I did that this morning before I came here, and I sent all these workers to do this for me. And maybe some of you felt uncomfortable when you were in bed, because you felt the trembling of the bed. And what I did is I started compressing the Earth because I wanted to bring it to a 2-centimeter ball to make it a black hole. So I tried to push all the mountains, all the oceans, all the cities, all the people close to each other. So now you're very close to a person who you like very much, but you're also very close to a person you hate. So be careful about it. So I was doing that this morning, and I reached this point. This is the Earth. Can you see it? It's black, because it's almost a black hole. So it's the Earth. I hope you can see it. It's the Earth compressed by me this morning, and all of you are here now. And so you're almost there. And I have a very expensive machine that I bought with the grant that I was given by the government to measure m divided by r of these things. So I will do that here. I have to put it here, and I have to press the button. And you know, it's like the one that you get in the market when they weigh the fish. Almost there. Okay, almost there. I need to press it a little bit more. Because it's the mass, and the smallest is the best. So let me see whether I get it. It was a 4, okay, now it's a 5. I'm almost there. So I have to do it one more time. Wait a moment. Some people know me because I'm a magician, so I have to do how do you want to do this? Because I do like that. And it's gone. Why is it gone? Because it's a black hole, and black holes are invisible. So it's somewhere here, but we don't see it. Okay. So that's how you make a black hole. But how do you see a black hole? How would you ever see a black hole? Well, some black holes are not alone in the universe. They are orbiting around a normal star. So this is this animation that shows you a normal star, like the sun, for instance, orbiting around the black hole. And because they are so close, mass from the star falls into the black hole, forms this disk around. This material gets very hot, millions of degrees, and you can see it emitting in the X-ray band. So you can see objects if you look in the X-ray sky. You can see black holes even if they're invisible, only if they have a companion. So I have this picture taken with an optical telescope in Chile, if I'm not mistaken, where Valentina comes from. And one of these objects is a black hole. Who can tell me which one is the black hole? Where? There? Okay. I move the finger just to see if there is another reaction. Okay, I don't know. It's not a quiz, but there is the black hole. And I just back and forth a little bit. This is optical, and this is X-ray. This black hole is called Cygnus X1, and it doesn't have any shape. We just see a bunch of points of light. We don't have the resolution to see anything. It's just a point of light source in X-rays. And it's in the position of a certain star here. And it's actually a binary star with a very big another star, very bright big star. So that's how you can see them. But how do you know it is a black hole? Well, you can do the following. You can measure its mass, because as I said earlier, Kepler came with this law. And he said in his laws, he says that the planets move around the sun, making an ellipse with certain properties, and they move around one time, I don't know, a period, and the distance between the two, and the masses of the two are all related. I don't give formula, not to enter into the nerd's status, but there are formulas that tell me what is the masses of these two things. The mass of the Earth is almost nothing with the sun compared to the sun, and if I measure how long it takes to go around, I can measure the mass. So I can measure the mass of the sun by doing that. But you can do the same. I don't have a nice picture, but okay, suppose you have a black hole and you have a star going around, and it's the same. You can use Kepler's law. This is my son, and I have to refuse it. Sorry. Okay. I hope he doesn't call it.
Very stubborn.
I hope this doesn't count against my time, because he will call again. No puedo atender, okay. And so you can measure the mass of the object. And then if you go and look, maybe there is nothing in that place. So how can it be that you measure mass of something and there is nothing? So I show a picture like the one Daan showed, but this is now the galaxy taken in the optical, a collection of all pictures of the sky, and I will go slowly zooming in into the center of our galaxy. This is our galaxy, looking from our perspective of the galaxy. And this is how it looks if you look in the infrared. Daan's pictures were much better. This is in the X-rays. It's a real picture, but of course, as Daan said before, these are not the colors in the X-rays because we don't see in X-rays. But these are false colors. But okay, it's true. If you zoom in there, this is what you see. Again, this is real X-ray observations of the center of our galaxy. If you zoom in more, now it's again infrared, and now it gives you more or less the scale towards the center of the galaxy. This is the dynamical center of our galaxy. And if you want to zoom even more, there are these photos made with infrared telescope. People who did this got a Nobel Prize, actually. And what you do is you measure over years, over a certain number of years, you move the orbit, you measure the orbit of the stars, like the Kepler thing that I said before. And by measuring that, so these are the measurements, and that is the, say, the animation of that. You can measure the mass of the object that is in the center. And I don't know I have the number, but the mass of that is about 4 million solar masses, 4 million times the mass of the sun. But it's obscure, there is nothing. If you take pictures, there is nothing. So there is a 4 million, a star is 4 million heavier than the sun, but there is nothing. It doesn't make any light. So if you could go in, this is now an animation, perhaps you would be able to see the black hole in the center. This would be the black hole in our galaxy. But why is a black hole so interesting? Why is it so appealing? We go back to Newton in his book of 1687. If you read the book, the whole book is about how to derive the laws of physics. But before he did that, in the prologue of the book, he had to say, define two things that he needed in the background to do the thing. He said, absolute space, these are his words, in its own nature, without relation to anything external, remains always similar and immovable. Well, it's a very cryptic phrase, but it means there is some space, and I don't care what you do, it's always there, and if you put a ruler, I can measure space in many directions with the ruler, and nothing will change no matter how many people are collected in the room, nothing. And then he said, absolute time, absolute true and mathematical time of itself and from its own nature, even more critical, flows equally without relation to anything external, and by another name is called duration. He said those things. He had to make a definition. He needed a system of coordinates, as we would say. So we needed to have that. But then it came Einstein, and he said, well, this is not true. I don't remember he had a phrase like that, but he concluded that absolute space and time do not exist. Actually, those two things are actually the same. And actually, the space is deformed by the presence of masses. And what does it mean, deformed? I cannot explain it. I don't know if a human being can explain it conceptually. But I make a little try. Because most of you might be nerds. You should know who Captain Kirk is, or must have heard. He's very old. But you must have known Enterprise, Star Trek, and all that. And he had this first official called Mr. Spock. And so in this example, Captain Kirk and Mr. Spock and the whole Enterprise are moving around in space, and they come across a black hole. And Captain Kirk says to Mr. Spock, let's explore it. Set yourself at a distance of 7 kilometers of that black hole and make an orbit, circular orbit around it. And the only thing you need to know is from basic schools is that the length of the circumference of the orbit is 2 pi times the radius. So if you do that calculation, which I don't know what it is, I don't know it by heart, it gives you the length. So Captain Kirk told Mr. Spock, okay, measure our length around the black hole and of the orbit, and now tell me how far away we are from the black hole, because if you measure the length, you can deduce the distance. And he said, okay, fine, so let's move now 1 kilometer inside and do the same. Let's do another orbit and measure the length of the orbit. And we can measure from there how far we are from that. It should be 2 pi times 6 kilometers now. But when they do the calculation, they don't get that. They get 2 pi point 6 times 6.08 kilometers. By the way, this is a black hole with the mass of the sun, because the exact number depends on it. So in reality, to get a circle of 2 pi 6 kilometers, you need to move a bit more than 1 kilometer. So you are at a closer distance, 5.913 kilometers, and not at 6. It's very strange. So you move, you think, okay, I move 1.08 kilometers, 7 kilometers, and actually I didn't move that. I'm still at 6 kilometers away. Something is very strange. Okay, the way to think of it is as if space is curved. And now, in which direction? Okay, I say it's curved and you think down, but it's not true. If you think in a two-dimensional piece of paper, and you draw circles in that paper, and the space was only two-dimensional, yes, it is bent down. But our space is three-dimensional, so the space is not bent down. But it looks like that, because you think you're moving 1 kilometer, but in order to be equally at the distance of 6 kilometers, you have to move more, because you have to move the extra distance to go down. It's longer to go down than to go directly to the center axis of things. Again, this is not how it happens, because our space is three-dimensional. You're not moving down. The problem is that to get, I always say it wrong, so I have to think about it, is I think to get 1 kilometer closer, I have to move 1.087. And if I'm closer, to get 1 kilometer closer, I actually have to move 1.106. And the closer I am, the more I have to move to get closer and closer. And that goes. So you continue going. This is like this. I just made this little drawing. It's if you're a kid in a sliding bank, and you think, okay, I'm sitting here and I want to reach the tree, I want to reach it from here, it's very nearby. But actually, to get there, you have to go all the way down. Again, in real life, this is not what happens, because the space is not two-dimensional, it's three-dimensional. But I cannot draw it, and no one in this room can draw it. Einstein could not draw it. So what happens? If you continue doing that, at some point you will reach a distance from the black hole where the speed of light is the escape velocity is equal to the speed of light. And if you're there, you're doomed, because you cannot move faster than the speed of light. You cannot even move close to the speed of light. But anyway, but if you're there, then you're done, because eventually you will be swallowed by the black hole. It's very bad animation, I know this now. The resolution is very bad, but okay, you're getting closer and closer. The Microscope is telling now, Captain Kirk, I think this is not wise, we should turn the engines back. And Captain Kirk is so curious that wants to continue, because he has a good contract with the TV sender that is making the movie, so he thinks, I'm not going to die. But okay, eventually, if you get close enough, not even Captain Kirk can escape. And then, Everyone know who Captain Kirk and Mr. Spock are, right? Yes. You're a nerd! There are other versions, I know. There is Picard, and later there is another one.
Wow. Thank you for the great talk. Is there any question? Yes? Question?
I was wondering, because sort of at the start you were talking about black holes orbiting, or other material orbiting black holes. Is it also possible for black holes to collide with any other matter? Because of the warping, it sounds kind of difficult.
No, it can collide. Actually, two black holes have collided and have been detected. The gravitational wave of the collapse of two black holes is spiraling one around the other until they merged and there was an explosion of light. Something happened. So those can eventually get close to each other.
And we have observed that over time as well.
We have seen the gravitational wave sources of two black holes orbiting around each other, yes. The chances that the black hole moving in the universe encounters another star and hits it like two cars hitting in the road, no, it's not very big. Because, for instance, I remember this when I was 16 or 17 reading books on astronomy, and they were saying, our galaxy is moving in the direction of Andromeda, the closest galaxy similar to us, and in so many million years we will collide. And they say, yeah, it's not going to be a catastrophe because the stars will not collide with each other. It's like two mosquitoes in the middle of the Grand Canyon and moving around, basically they will not collide. Okay, there will be an attraction and there will be an effect. There will be some disruption of the movements of the stars, fine, but not that they will collide. So that the black hole moving around in space goes beyond the red light and crashes another car. No, I don't think that.
Any other question?
Well, my first year students of physics, astronomy that came especially to see me.
Oh, there is a question here.
So the warping is because of mass, and particles have mass, but antiparticles also have mass. Could there be antiparticle black holes?
What do I say? I don't know. That I don't know. Okay, there is an aspect of black hole physics that is mathematical physics. There is a group of astronomers, of physicists, in the Institute where Daan works, there is a couple, where they studied the physics of mathematical movement of mass like did Hawking did. I don't do that. I explain it in a nice talk, but I do observations of X-rays. So I don't know those answers. What I can guess from my memories of the cosmology courses is that the relation between matter and antimatter apparently is very asymmetric. There is a lot of more matter than antimatter for some reason at the Big Bang. I don't know why, but that happened. And so the chances that we see a structure made of antimatter, a galaxy made of stars of antimatter, but in principle I suppose it could. But okay, I should not be quoted on this.
Yeah, it's recorded.
I know. People are listening and then they're now putting it on Facebook. Or whatever is TikTok.
Any other question from the audience in the back?
There is a hand there.
I don't see it.
Yeah,
I'm very short, sorry.
Since black holes are confirmed to exist, do we know if white holes also exist?
Since black holes what? Are known to still exist? Yeah. Do white holes exist? I don't know. I think it's a bit of speculation that you would see a white hole is like this, these tunnels where you enter a black hole on this side and you exit a white hole on the other side. I don't think that there is any observational evidence. I'm an observer. I'm observation astronomy, so I like to manage data. And I don't think we have seen anything that looks like that. All these fantastic ideas of traveling through these wormholes and appearing on another, yes, could be, I don't know. I don't even know if you would survive if you enter one hole. And the white holes, I cannot tell you. I don't know. I don't think there is any evidence. No one wrote a paper that I know of. Oh, wait. Maybe she knows.
Do you know?
No, I don't know, but I have a question.
Okay, no, go ahead.
Okay, my question is because you said that you just observe and so on. I wonder if you would try to solve black hole information paradox, how would you do that?
Information paradox. Information paradox, right?
Yes.
I don't know how I would solve it. There's no way I can solve it. What I understand I'm probably even worse than some of you on this, but what I understand is from Hawking's ideas is that if you have a black hole, they eventually emit, although they should not, they emit, because what happens is you have this particle-antiparticle created over a very small space, a Planck distance is called. But if they are very close to the black hole, it can happen that when they create, before they recombine, one of them falls and the other one moves away. Yeah. And if you look at it, it's like if an antiparticle goes in and a particle goes out, it's equivalent to a particle coming all the way out. And so something escapes the black hole, and so he thinks that the black holes can evaporate. I think you are going along those directions, right? Yeah. I don't know the answer to the question, but I wanted to say something because it sounds so bad. If you are the speaker and you say nothing, I don't know, so I wanted to say something. But I don't know how to answer your question. It's a good question, I don't know the answer. There was another question.
Yes, another question.
So I speak with my son, who's 7 years old. I speak to him about the black holes because he likes the subject, but he's a bit scared of them. Is there a possibility that the black holes won't end the universe as we know it, or is it inevitable?
Well, the black holes will not end the universe. As I said to a question around here, I think it's very unlikely that a black hole will hit another star. It's very unlikely that we are going to be hit by a black hole. What we don't see, we don't know. So we don't know all the black holes that we don't see. The ones that we see, because they are with the binary with another star nearby that makes them emit, the density is not terribly high. So it's not that we expect a lot of them. I think he wants to answer the question again, or he wants to hit me. You wanted to hit me.
I want to hit you, yes. Next Chris Rock.
No, but I don't think we will be, I would not worry that we will be killed. Anything can happen, but I wouldn't be worried that we are going to be hit by a black hole.
Wasn't there a supercomputer that just sort of said it was inevitable that black holes will just absorb the whole universe in the end, like after a quadrillion years?
No, I don't know. You're entering the topic of the previous talk, is whether the universe is now expanding. Yeah. Will it ever collapse again? And a few years ago there were these theories that said the universe expands, then there will be a big crunch, everything will come back. But apparently what they find now is that the expansion rate is exactly the one that will make it expand forever, but at infinite time, it will stop at infinite time. So you can go very fast, very slow, and then collapse again, or exactly at the speed at which it will slowly slow down, and never stop at infinite stop, exactly stop. And that is very high Q, but apparently what I hear that's what they find. There is another question behind me.
Yes?
Yeah, sorry. I guess I was wondering if there's also a system in the Milky Way where you have two stellar mass black holes and then a third star orbiting around the system, and how difficult it is to get them.
Two stellar mass black holes with another star going around. Well, I don't think it's impossible. The problem with that is stability. There are some triple systems we know where you have two stars orbiting very close to each other and then another star orbiting far away. And even in some cases, people think, looking at what you see from the light curves, you have a neutron star, for instance, and you have a normal star, and then you have another normal star, and you see also variations in the light curve that indicates that configuration. And in principle, it's not impossible, because in the evolution of these two stars in the binary, one can explode as supernova and produce a black hole, the other one can explode later as supernova producer, and then you end up with those two black holes. And depending on the environment where they are sitting, they might be affected by perturbations of other objects or whatever. You know, three-body problem is unstable. Unless you're in a very special configuration where these two are orbiting and this one is orbiting very far away. It's not impossible, but the problem is that if you have these two and this is far away, no matter from this one will follow to this one. Understand? Because it's really far away. If they are very close, when you have the stars very close, even before they could form a black hole, they will probably disrupt because the system is unstable.
Any other question?
On my second speaker. So if creating a black hole only depends on the range between mass and size, then you have arbitrary small or arbitrary like large black holes. There are limit on the how big or how small can they be.
I think in principle there is no limit. There are the big black holes that you probably know of because that's how the kind of objects that you study. Although you're interested in the dark matter part probably, but the black holes are in those galaxies. At the center of our Milky Way we have a black hole of 4 million solar masses, and in other galaxies like the one that they made a picture of the rings around the black hole a couple of years ago is 10 to the 9, so a billion solar masses. And there are black holes like the one that I showed the X-ray picture that I flipped optical X-ray, that is about 10 times the mass of the sun, and there are black holes that perhaps have 5 times the mass of the sun. So in that respect, they are small from the mass of the sun to a billion times the mass of the sun, so everywhere there. And then theoretically, you could have primordial black holes that are very small, of course. And if black holes evaporate, following the information paradox question that I was trying to mumble something about, particles escape. As I said, one antiparticle goes in and the other one goes out. That is equivalent to particles going out. So by doing that, the mass of the black hole decreases from the black holes over a very long time will evaporate. So they could be very small black holes. I know that giving this talk brings people asking me these questions about the mathematical aspect of the theory of physics of black hole, which is not my field of expertise, but okay. And because you are astronomers or astronomers to be, it's more difficult to just tell you anything and then
Okay, well, if there is any more question for the speaker. Oh. I didn't want you to do that.
But you didn't, so
yes.
The last one. You should
last one. Okay, I'm sorry. Yeah, it's terrible to have reports. Yes.
No, it's fine.
I just thought about it right now, so sorry. I was thinking about the question of the black holes absorbing every matter and ending our universe, and even though the space is expanding while the matter is finite, can it be that all the possible matter will be indeed absorbed by the black holes, and even though the space is expanding, the newly space will be filled only with those black holes that will grow enormous in size and
well, the universe will not, but okay, let me say it this way. If you are very far from a black hole, you don't know it is a black hole. It just behaves like a normal star. We are very far away from the black hole at the center of our galaxy. It is 4 million times the mass of the sun, and we don't know. Nothing strange happens to us because of that. We are still orbiting around the center of the galaxy, I think at 250 kilometers per second, without noticing anything special. It could be a black hole there, or it could be a 4 million times the mass of the sun star that does not exist, or 4 million stars with the mass of the sun all together in a balloon. I don't know. For us, we are so far away that for us it's the same. It doesn't really matter, and that is because Newton's theory is an approximation to Einstein's theory under certain circumstances. So if you're very far from the black hole, Newton and Einstein are the same. If you're moving very small velocities, Newton and Einstein are the same. So for us, the black hole in the center of the galaxy is just, it doesn't affect us. Suppose that you even put all the mass of the galaxy from, if you know physics, you know what I'm talking about. If you put all the mass of our galaxy that is inside the circle of the sun, you put it in the center, or you put it distributed, spherically distributed actually, it's the same. You don't see any difference. You can put everything in the center or everything. So now what you can do is you can take all the mass around around the center of the galaxy and make it fall into a black hole there, and then you have a black hole at the center, and we are still at this distance, we don't know. I'm saying if you could do that, I don't know how, but if you could do that, you wouldn't know. So actually, I wouldn't worry. Actually, not even your children will, your grandchildren or anything, if that will ever happen. Okay, I think Valentina didn't want more questions, so I thank you very much.
Yes, thank you. Okay, so now we take another break for more beers, and you should start making your teams for the